All right, I'm going to close this question in 5, 4, 3, 2, and 1. Okay. I know I do not have 90%. No, actually I do. Anyway, but I'm going to reopen this anyway, okay? So here are our responses. 3 of them, 2 of them, okay? So most of us selected only 2 of them. Now we'll reveal the answer a little bit later, but not now. We'll get there in a second, okay? Now, give me like 15 minutes to get to that slide. But before that, I just want to remind us what we've been doing, okay? So towards the end of last Thursday's lecture, we started talking about nucleophile strength, okay, and how it affects SN1 and SN2 reactions, okay? So we saw that nucleophilicity or nucleophile strength does not affect the SN1 reaction, yeah, right? It doesn't affect the SN1 reactions. The reason is, okay, in SN1, the nucleophile does not participate in the rate determining step, okay? And then for SN2, because you have both nucleophile and electrophile involved, the reaction rate depends on the nucleophile strength. So that's what we have. So some of you asked me about, how do we determine the strength of the nucleophile, okay? We are not going to go into details about this yet, in this class, but you will in your OChem class, okay? But for now, what I want you to know is this. Nucleophilicity or nucleophile strength is proportional to the basicity. Especially this is true when the charge bearing atom or the lone pairs are lone pair bearing atom is in the same period. Okay, that is it. So we know how to determine the basicity or base strength. All you had to do was use that to determine the nucleophile strength. That is it. That's all you're going to be tested on. If there's a question, from that. Okay. So here's an example. I'll open this. I had to skip a question, but it's okay. All right. We have more than actually close to 100% answers. I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here, that's beautiful. Oh, this is a new way of, presenting questions on TopPad. I just want to try it out. And that's why my math thing did not work here, like, subscripting. Anyway, that's fine. So, yeah, I agree. Now, most of us said the CS3O minus, or this guy is stronger than this nucleophile. The reason is these electrons in the negative charge, okay, they are delocalized because this negative charge is one bond away from a double bond. Because of that, those electrons are less available to attack an electrophile. Okay. On the other hand, in the stronger nucleophile, which is this guy over here, you don't have that double bond, one bond away from the charge bearing atom, meaning it is more available to attack something. Okay. Therefore, this is going to be the stronger nucleophile or the more reactive nucleophile. That's the idea there. All right. What questions, concerns, comments do we have? This is the same idea. By the way, the nucleophiles are also kind of bases, right? So when we say, when we talk about Lowry-Bronsted bases, we're talking about, grabbing a proton. Okay. But when it comes to Lewis bases, which we will talk about somewhere else, not in our curriculum, okay, you see that what they do is they use their lone pairs to attack positive charges around them. Okay. And nucleophiles are such bases in a way. All right. Any other questions, concerns, comments? I'm done with, unit 7. This is just tying up a loose end. That's it. Any questions, concerns, comments? Okay. I could have easily skipped this, but I know I decided to do this for a reason. I hope that you will figure it out. Okay. Now I'm going to clear my doodling. So with that, if you see a blue, okay, I don't want to talk about it. Anyway. So I have an electron in my, I had an electron in my backpack, but if you see it somewhere, please let me know, okay? I don't seem to find it. All right, found it. Okay. All right. So with that, let's do this. The last unit of the semester. Oh, we're done. Okay, by the way, you guys really did well when it comes to the class survey. Last time I checked, we were around 89%, which is close enough, okay? But if you haven't done it yet, okay, I mean, other 10%, please do them, okay? I'm kind of, I want them. I want everything. All right. So let's do this. All right. So again, this is the last thing I'm going to teach you this semester, probably, most probably. Okay. So I really hope that you will pay attention for a second. Okay. So this is what I want you to do. I'm going to try to do my, here we go. Okay. So let's talk redox. Okay, reduction and oxidation, that's what is meant by redox. So let's talk about it, okay? So I'm going to do this for an example, okay? If you can pay attention for a second, you will be really happy by the end of today's lecture, okay? So anyway, so let's think about magnesium reacting with oxygen to produce magnesium oxide. Okay? I omitted the phases. Yeah, I don't care about that for at least for now. Okay. Now, what I want to know is what happened to magnesium and what happened to oxygen during this reaction. Okay. Now, here on the reactant side, what is the charge of magnesium? Everybody. Okay, one more time. Do it on your whiteboard so that I have a better chance of getting you to work here. Okay. So, what's the charge of magnesium on the reactant side? I'll give you 10 seconds. Go ahead. One more time. What is the charge of magnesium on the reactant side? Mg. What's the charge of that? Do not overthink this, okay? I mean, please do not overthink it. Okay. On the reactant side, what's the charge? All right. Can I see a white base one more time, everybody? I hear. Thank you. I see one correct answer. The others, only one so far. Only one. Is it 1 or 0? 0. Okay. Thank you. Two correct answers. Thank you. 0, right? Magnesium on the reactant side is not bonded to anything else. Okay? It doesn't have a charge. You said. Why did you give it a charge if it doesn't have a charge? Okay? Do not assume things, all right? So here, John, right? It doesn't have a charge, right? Yeah? Ian, do you agree? Yeah? It's 0. Don't overthink it. Okay. So charge here is 0. Now, one more time, the same exercise, but this time on the product side. What is the charge of magnesium on the product side? Go ahead. All right. Can I see a whiteboard, everybody? I want to see a whiteboard. Lauren, I want to see the whiteboard. What is it? What's the charge of magnesium on the product side? Lauren? Thank you. Thank you. Yes, it is +2. Right? It is +2. How do we know? Magnesium in an ionic compound forms +2 charge. That's it. Okay. So the charge here is +2. Okay. Now here's what is important for us. Okay. Now we see that the charge of magnesium, by the way, this charge also referred to as oxidation state. Okay. So this is also known as the oxidation state. You see that the oxidation state of magnesium has increased or decreased. It has increased, right? So it has gone from 0 to +2. Okay. So in other words, oxidation state has increased, and that is known as an, what do you think? This is called an oxidation. This is an oxidation. So magnesium is oxidized. Let's say oxidized. Let's say oxidation. What do you want to do? Let's say oxidation. Let's say oxidation. I'm sorry about that, but I changed my mind. Let's say oxidation. Okay. Now let's do the same thing for oxygen, right? Oxygen is bonded to the same atom here. So therefore, the charge of oxygen or the oxidation state of oxygen here is 0. What is the charge of oxygen on the product side? Everybody? -2, right? So the oxidation state of oxygen has increased or decreased? Yeah, it has decreased. Okay. And that is known as a, okay, not that, creative here, a reduction. Okay. So you see that one species has been reduced while the other one is oxidized. Guess what? These are known as reduction oxidation reactions. Okay. Reduction oxidation reactions. This is too much to read off, So let's take red from reduction and OX from oxidation, and let's call this redox. Redox reactions. This is it. This is what redox reactions are all about. One is getting oxidized, the other one is getting reduced. That's it, done. Okay. What questions, concerns, comments do we have? Anything? Now, yes, Caroline, can you have the mic? Do you have a microphone? Thank you, Aiden. Caroline, go ahead.
I get why O2 would be like a 0 charge because you have the 2 oxygen molecules, but why?
The atoms?
Yeah, atoms. But why would magnesium is just the one atom? So how would it be canceled out? Why wouldn't it just be the charge that it has?
It's not canceling out. It's not bonded to anything else. So there's no way it can have any charge, right? It's by itself. It doesn't mean that it is we only have one atom in nature. They are going to be, together with other magnesium, atoms, okay? But it is still 0 because it's not bonded to anything else. Same with oxygen, okay? Oxygen in O2, it's bonded to the same atom, therefore it's going to be 0.
It only has charge if it's being bonded.
Bonded to something else.
Okay.
Yes.
All right.
Yeah.
Thank you.
Any other questions, concerns, comments? All right. Now, here's the other thing, Ileana. Here's the other thing that we need to appreciate here. Okay. So for magnesium to oxidize, okay, oxygen has to be there. Okay, oxygen is what is oxidizing magnesium. Okay, and same way, now for oxygen to be reduced, magnesium must be reacting with it. Okay, so magnesium is what is reducing oxygen. Okay, so for that reason, in this reaction, I'm going to try to use a different color if I have a different color. For that reason, magnesium in this reaction is referred to as, because it is reducing oxygen, it is called the reducing agent. This is the reducing agent. Okay. On the other hand, oxygen is the one that is oxidizing magnesium. Therefore, oxygen is referred to as, anybody? Thank you. This is called as oxidizing agent. Oxidizing agent. Okay. So it is like this. Okay. Say that I'm going to undergo myself, going to undergo a redox reaction. I cannot do it by myself. Okay. So I asked, I don't know, somebody like Annie, do you want to be my oxidizing agent? Yeah. So what I'm going to do is I have my electron. Okay. I'm going to pass it to Annie. You got it. Okay. Now, what has happened to me? I am missing an electron. So I have a +1 charge, right? I have a positive charge. My oxidation state has increased. Okay. And on the other hand, I have given my electron to Annie. So what has happened to Annie? Annie has been oxidized or reduced. She's been reduced because she has a negative charge now. Okay. So I am the reducing agent because why? I am the one who reduced Annie. On the other hand, Annie is the oxidizing agent because of Annie, I'm oxidized now. Okay. Same thing is happening here. Yeah. Thank you, Annie. All right. What questions, concerns, comments do we have? Anything? Any questions, concerns, comments about what is being oxidized, what is being reduced, oxidizing agent, and reducing agent? That's all we have talked about today. This is all we have to talk about today anyway. Anything? All right. Now, I'll show you some common patterns that help us to identify the oxidation states. Okay. Now, if you have like, element by itself, like magnesium, we know it's going to be 0. Oxidation state is 0, right? So I can actually boil it down to some patterns like this, right? So if we have elementary substances, meaning pure, elementary means pure substances. It is not bonded with anything else. Okay, it is bonded with the same thing or not bonded at all. Okay, for example, O2, O3, aluminum, copper, magnesium. Okay, if they are in their elementary stage or elementary substance, okay, and this will have an oxidation state of 0 because it is not bonded to anything else. Okay, and also if you take monoatomic ions like oxide or chloride or fluoride, okay, let me actually write some of these as well. Okay, so like fluorine, okay, chlorine, okay, or a sodium plus, or I don't know, you can think of calcium 2 plus. Okay, so if you have monoatomic ions like this, their oxidation state is their charge. For example, the oxidation state of fluoride O minus is -1. The oxidation state of calcium 2 plus is 2 plus, and so forth. Okay, those are some observations. Okay, it's pretty kind of intuitive as well. I just want to, mention them. Now, there's something else that we need to do that is kind of the newest thing that the only new thing that you'll be learning today. Okay, main new thing that you'll be learning today, and that is when we are dealing with, let me clear this, when we are dealing with organic molecules. Okay. So when we are dealing with organic molecules like this, please ignore this part for the moment. I don't like it, but you know what? Let's take this molecule. Okay. Now, if we should be able to assign oxidation states to each and every atom in this molecule. And you will know how to do this by the end of today's lecture. Okay. All right. I'm going to switch to my notebook and then come back to this. Okay. So here's how we do it. This is fun. I really like this part because I get to, label the atoms. All right. All right. This is how it goes. So let's think about the same molecule we had before. We had ethyl alcohol or just alcohol. If you go to a bar on Friday, they offer you this. If you pay them money, of course. Sometimes you get free drinks. I've never got a free drink. Anyway, anyway, it's a different story. I don't want to talk about it. So, okay. Now let's think about how to handle this. Okay. So let's say that we want to determine the oxidation state of this carbon over here. I'm going to say this is carbon A and carbon B. Okay. we'll deal with carbon A now. Okay, this is how it goes. Now, between carbon and hydrogen, which atom is more electronegative? Carbon is more electronegative, right? Therefore, the bonding electrons of the carbon-hydrogen bond will spend more time around carbon or hydrogen? Carbon, right? This is what I'm going to do. I'm going to say these electrons are going to spend more time around carbon like this. Okay. Same thing with this carbon-hydrogen bond, and same thing with this carbon-hydrogen bond. Okay. What I'm meaning is all the electrons in that bond will spend more time around carbon than hydrogen. Bad deal for hydrogen. All right. Now let's think about the carbon-carbon bond. Okay. The electrons of this bond will spend more time around carbon atom A or B. What do you think? It's going to be a split, right? So I'm going to split it in the middle like that. Now I'm going to start counting, okay? So from the carbon-carbon bond, my carbon is going to get only one electron. From the carbon-hydrogen, you're going to get 2 electrons each. Okay? So right now, I see that I have 1, 2, 3, 4, 5, 6, 7 electrons around my carbon atom. Originally, when it was neutral, it had how many electrons? 4, right? It only had 4 valence electrons. Okay? Originally, it had 4. Now I have 7. That means I have 3 more electrons than before. Meaning, my oxidation state, or I have a -3 charge because I have 3 more electrons than when I was neutral. Okay? Therefore, the oxidation state of this atom is -3. Okay? This is how we do that. Now, let's do the other one as well. So this is the oxidation state of this carbon. Carbon atom B. I'm going to do this now because I'm going to, give you plenty of practice problems after that. All right, let me do this. Now, carbon-hydrogen bond. Carbon is more electronegative. Therefore, carbon is going to get the electrons of the carbon-hydrogen bond. Okay. With the carbon-carbon bond, it's a split. You're going to get only 1 electron. With the carbon-oxygen bond, who will get the electrons? Oxygen or carbon? Oxygen. Therefore, I'm going to draw the thing this way. Carbon is not going to get it. Okay. Now I'm going to indicate my electrons, 2 from this, 2 from this, 1 from this, and none from the carbon-oxygen bond. Okay. Now, if I count the electrons, we have 1, 2, 3, 4, 5 electrons around it. When it was neutral, we had 4. Now we have 5, meaning I have 1 extra negative charge now. Therefore, my oxidation state is -1. Okay. So -1 is the oxidation state of carbon atom B. One more. I'm going to do one more. Okay, just for fun. All right. Now, oxygen. Okay, let's do oxygen oxidation state just for fun. Oxygen, by the way, tends to have the same oxidation state in any molecule, but let's do this again here anyway. All right. So we know that we have 2 lone pairs here. By the way, you know that we have 2 lone pairs here as well. Don't forget those 2 lone pairs. Okay. Now let's see. So from the carbon-oxygen bond, oxygen will get the 2 electrons of the bond. From the oxygen-hydrogen bond, oxygen will get the 2 electrons. Okay. Right now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. We have 8 electrons now. When it was neutral, it had 6 valence electrons. Okay. Guess what? I have 2 extra negative charges. Therefore, my oxidation state is -2. So oxygen is -2. By the way, oxygen almost always form -2. I mean, there are exceptions, of course, but usually it is -2. All right. And then if you wonder about the hydrogens, any of these hydrogens, let's do that as well, just for the completion. Okay. Hydrogen has 0 electrons now because all the electrons will spend more time around the other atom, right? It has 0 now. Okay. It had 1 to begin with. 1 minus 0 is +1. Okay. So it has 1 to begin with, 0 now, meaning it has lost an electron. Therefore, the oxidation state of hydrogens are +1. That is true for all my hydrogens. There you go. This is it. This is all you had to do to determine the oxidation states of the atoms. All right. What questions, concerns, comments do we have? All right, let's have some fun. Okay. So, Ian, any questions for me? Yes. Andrea, you have a question? Yeah, give me a second, Andrea. Andrea, here you go.
How did you get the neutrality of like the carbon and oxygen?
How did we get what?
The neutrality, like the 4 and the
So
6.
neutral means when it is an atom not bonded to anything.
Mhm.
Okay, that's when that is the charge when they're neutral. It's zero, right? I mean, for an example, carbon when it is neutral, it had 4 electrons. How do we know it? Carbon is in the 4th group in the periodic table.
Oh, right.
Yeah, that's the number of valence electrons.
Okay. And oxygen is in the 6th group. Okay.
So, yeah, exactly. Hey, keep the microphone, and I'll come back to you. Ian, you have a question. Thank you.
Now that we found the charges or the OS
Solution states,
of each one, what can you do with those?
Yeah, so what are we going to do with them? We're going to see during a reaction if they change or not. If they change, they undergo redox reactions. Yeah, we'll practice that. All right. So with that, let's do this. Here we go. Here are some molecules. I want you to determine the oxidation state of each atom. Go ahead. Just for practice. Any
But one of them was already there.
All right.
You're only
And let me see your responses just for fun. Okay.
and then
Hydrogen +1, oxygen -2, chlorine -1, and carbon of H2CO, which is this guy over here, is 0. And then oxygen of, oh, I'm sorry,
then
oxidation state of carbon of CO2 is +4. Only 151, 75%. Why is that? Okay. So that means I'm going to do carbon dioxide. Okay. And again, this is what I'm going to do. Please pay attention for a second. So
I know
carbon oxygen bond, because oxygen is more electronegative, these electrons of the bond will spend more time around oxygen rather than carbon. Okay. Therefore, we get 1, 2, 3, 4 electrons from the 2 bonds to this oxygen. Therefore, now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. This is what we have now. This is what we have. Okay. And then when it was neutral, it is not here. When it is neutral, we know oxygen has 6 electrons. A learning assistant, if you can walk to the tables who are still, discussing, can you help them out? They're discussing chemistry, I know. So go to those tables and, make sure that they, understand it. Okay. Thank you. All right. Now, this is what oxygen has now. And when it was neutral, it had 6. How do we know? Oxygen is in the 6th group over here, which has 6 valence electrons. That's how I know it. Okay. And therefore, if I can move this back again, okay, I'm going to write 6 here. Okay. This is what we had when it was neutral. Neutral. Okay. We have 2 more electrons than it was neutral. Therefore, we should have a -2 charge on this oxygen. Okay. On the other hand, let's think about carbon. So in the carbon-oxygen bond, carbon gets nothing. Okay. Because oxygen has a high electronegativity. Therefore, bonding electrons will spend more time around oxygen rather than carbon. Okay. Now, as a result of that, this carbon has 0 electrons. 0 is what we have. Okay. We had 4 when it was neutral because carbon is in the 4th group. 4 when it was neutral. Okay. Therefore, we have 4 less electrons, meaning +4 charge. Or 4 minus 0 is +4. Okay. So the oxidation state of this carbon is +4. That's it. All right. 20 more seconds. Please submit your answers. Caroline, you're doing okay? Yeah? Okay. All right, so I have close to 90% answers now. Okay. Meaning I'm going to close this question in 5, 4, 3, 2, and 1. All right. So here's what I'm going to do for this one. Okay. I'm going to try to do this myself, and hopefully I'm going to make a mistake, and then you're gonna point that out. Okay. So let's do this. So this one is easy, right? So oxidation state is for monoatomic ions. The oxidation state is the charge. Okay. So this should be -1. There's no doubt about that, right? And also, if you want to confirm that, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around chlorine now. When it was neutral, it had only 7. We have 1 more electron than when it was neutral. Therefore, it should be -1. That's the other way to look at it. Okay. And then in this case, oxygen hydrogen bond, oxygen will get all the electrons. Therefore, oxygen has 8 electrons around it, meaning it should have -2 charge. Why? It has 8 now. When it was neutral, it only had 6. It has 2 more electrons than when it was neutral, meaning it should be -2. Okay. And on the other hand, hydrogen is 0 electrons now. It had 1 to begin with. It has lost its electron. Therefore, it should be +1. Okay. And you see that if you add this up, -2 plus 1 is -1. That gives you the overall charge. Okay. And last one, so oxygen is, okay, this is, oxygen will get the electrons of this bond, oxygen will get the electrons of this bond, and carbon will get the electrons of this bond. Okay. So oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons now. Therefore, this should be -2, just like before. Same thing here. Oxygen has 8 electrons now, meaning this should be -2. Okay. Carbon has only 2 electrons now. It had 4 to begin with. It has lost 2 electrons. Therefore, its charge must be +2. Oxidation state must be +2. Hydrogen had 1 to begin with, has lost its electron now. Therefore, this should be +1. Now, if we add the oxidation states again, +1 plus +2 is +3. +3 -2. +3 plus -2, and -2 is -1. So if we add the charges up, it will add up to the overall charge over here. That's it, done. All right. Yes, John, thank you. Reopen? Yeah, I'll reopen the questions. That's fine. No worries. All right. What questions, concerns, comments do we have? Anything? So here's what I'm going to do. I'm going to do one of them. Which one do you want me to do? KMNO4. Thank you. Okay, I'll do it. All right. I'm going to do KMNO4. You're going to do the rest. Okay. So let's see if I can do KMNO4. By the way, because this is easy, I'll do this as well. This is 0. Okay. It's easy. It's right there, right? Why not? All right. So to do this, I know these are my metals. They will form plus charges. And I know my oxygen is must be my negative charges. I have 4 of them. Oxygen usually from -2. I have 4 of them. So this side must be -8. Why? Oxygen is forming -2. I have 4 of them. 4 times -2 is -8. Therefore, this side must be +8. But I know potassium can only form +1 because, because it's in the first group. But magnesium is, manganese, I'm sorry, not magnesium. Manganese is the wild card. Why is the wild card? Because it is a transition metal. If you can remember from 151, the oxidation states or charges the transition metals can form is redonkulous. They can form more than 1 charges, okay? So now, but we know the overall charge on this side is +8. Because this is +1, manganese has to be what? +7. There you go. Done. All right. So I'll do SO32- on the screen so that you won't overcomplicate things. All right. This is how I would do it. Okay. When in doubt, think about how would Pereira do it. Okay. So now Oxygen, I know, form -2, right? So we have three of them. 3 times -2 is on this side. It should be -6. Okay. Now I want my overall to be -2. Therefore, my sulfur has to be plus what? +4. That's it. Done. Do not overthink this. Do not try to, I don't know, you can draw the Lewis structures if you want, but you don't have to. Okay, this is all you have to do there. Get it? Yeah. All right, 20 more seconds. Please submit your answers. All right, so and how's it going? Chris?
Yeah.
I'm pretty sure he's lying. All right, so I'm gonna close this in about a minute. So let's see if I can do H2CrO4 while you are doing that. Okay, under a minute. Okay, so oxygen is -2. You have 4 of them. It should be -8. Okay, and then hydrogen is, let's say, you have 2 of them +2. Therefore, this should be +6. Done. Oh, it's under 30 seconds, I think. Right? All right. I'm going to close this question in 5, 4, 3, 2, and comes after that. It should be 1. Here we go. And here are our responses. Yeah, it's okay. I mean, I think NO3 minus was the issue. Why is it an issue? Okay, anyway, NO3 minus, oxygen is -2. You have 3 of them. Therefore, this should be -6 on this side. For you to have overall -1 charge, my nitrogen must have a +5 oxidation state. That's it. Right? And this is how we get overall -1, because +5 plus -6 is -1. All right, I have close to 80%, 90% answers. Okay, I'm going to close this question in 5, 4, 3, 2, and 1. All right, really quickly, okay? So first reaction is a redox reaction. How do we know? We are going from, so this is 0, right? Both of them are 0, okay? And then nitrogen over here is a -3. Anyway, so you can figure it out, right? So nitrogen is a -3. Anybody who's determined that? -3, right? -3. Therefore, nitrogen has been reduced and hydrogen has been oxidized to +1. So we know that's a redox reaction. Okay, anyway. And then reaction 2, business end. I only think about the business end, okay? Do not worry about all the other atoms in a molecule. Think only about the business end, meaning where change occurs, okay? The change occurs here and here. So oxygen, let's think one of them at a time, okay? So let's think about this. So here's what we have here. And we have lone pairs, and then all the electrons of the 2 bonds will spend more time around oxygen, meaning oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons, meaning it should be -2 here. Okay, and even here we have a negative charge now, meaning we have 1, 2, 3, and then carbon is over here. The carbon electrons will spend, carbon oxygen bonding electrons will spend more time on oxygen as well, meaning we still have 8 electrons around this oxygen, meaning the oxidation state is still -2. The oxidation state has not changed in the business end, meaning this is not a redox reaction. It hasn't changed. If the oxidation state has not changed, it hasn't undergone a redox reaction. Okay, so this is not redox. Okay, now third one. So carbon, chlorine. So let's think about this carbon. This is my business end. All right. So the carbon, carbon, and carbon, chlorine, and that's this carbon, hydrogen as well. Anyway, that's fine. Anyway, so this should be a split. This should be a split. Carbon, hydrogen. Carbon gets the electrons. Carbon, chlorine. Chlorine gets the electrons because chlorine is more electronegative. Okay. Right now we have 1, 2, 3, 4 electrons around this carbon, meaning oxidation state is 0. It's neutral. 4 when it is neutral. 4 we have now, meaning it oxidation state has not changed. Okay. Now let's look at this carbon over here as well. Okay. So carbon carbon is a split, 1 electron each. Carbon hydrogen, carbon gets the electron. Carbon oxygen, oxygen gets the electrons. Okay. Again, we have 1, 2, 3, 4 electrons, meaning oxidation state is still 0. Therefore, oxidation state has not changed. Therefore, this is not a redox reaction. Okay. Last one is a redox reaction. Okay. So we had carbon hydrogen. Let's think about one of them. Okay. And here we only have carbon, carbon. Okay. So this should be a split, meaning we have 1, 2, 3, 4 electrons around this, meaning it should be 0 here, oxidation state. But in here we have 1, 2, 3 splits. And carbon hydrogen, you're going to get all the electrons of the carbon hydrogen, meaning we have 1, 2, 3, 4, 5 electrons, therefore it should be -1. Right? So we are going from -1 to 0. This is an oxidation. Oxidation state has increased, therefore it's an oxidation. And then hydrogen must be reduced, therefore this is a redox reaction. Isha.
For 2, why didn't we look at NH2?
Come then again?
For the second one, why didn't we look
We
at
can. I mean, we can look at only one business then. It's same thing. You will see that it hasn't changed.
Okay.
Huh?
And the same
Yeah.
goes for OH and
Yep.
yeah, okay.
Yeah. If you look at just one, I mean, it should tell you the whole story. All right. One last question, then we are done with everything. Oh, by the way, let's check my answers. Okay. So, don't forget your line to Lewis conversions. Okay. It might be useful. Maybe. I don't know. So they're talking about carbon atom 2 for the sake of time. Let's do this. Here's this carbon atom. You have a carbon, carbon, and carbon here. So if I split the electrons, because all of them are carbon-carbon bonds, they are all split. Meaning we have 1, 2, 3, 4 electrons around carbon. It had 4 to begin with. Now we have 4s as well. So the oxidation state has not changed to be 0. So this carbon over here, okay, let's see what has happened. So we have, I need to switch, I'm sorry. Switch colors, meaning, right? So we have a carbon, 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 okay? Carbon, carbon is a split, carbon, carbon is a split, carbon, carbon is a split, carbon, chlorine, chlorine is more negative, therefore chlorine will get the electrons, okay? Now we have 1, 2, only 3 electrons around this carbon, okay? So meaning it has lost 1 electron, meaning it should have a +1 charge. Otherwise, look at this we have 3 now, we had 4 to begin with, 4 minus 3 is +1, okay? So this should be +1. So oxidation state of this has increased from 0 to +1. So this should be an oxidation. That's it. All right. So that would be it. Here's the attendance code. I'll see you on Thursday for reviewing. Okay. Bye, everybody. John.